Believe it or not, we're up to Chapter 11 now, the last chapter of coverage. Section 11.1 is called Goodness of Fit, and I thought that I would actually lead into this with a motivating example. Chairwoman Chandra believes that the ideal grade distribution throughout the UMGC math department should be 10% A's, 30% B's, 30% C's, 20% D's, and 10% F's. Yes, the chairwoman actually believes that 10% of the students should fail the class. She randomly samples 40 grades from last semester and finds that they are distributed according to this table. So this is our empirical observation. We found 8 A's, 18 B's, 12 C's, 0 D's, and 1 F. Does the ideal distribution appear to be a good fit for the real grades? And we're going to test this at the 0.01 significance level. If not, which grades seem to be most over or underrepresented at UMGC? Now, Chairwoman Chandra is very sophisticated. She understands sampling error. So she knows that even if these percentages turn out to be a little different from the ideal, that's not cause for alarm, because all samples are a little different, and no samples are really a perfect match for the population. But there comes a point where if this distribution is very different from the ideal, we can conclude that they're not a good fit at all. So, of course, that's what hypothesis testing is for, is to determine if there's a difference here between the actual and the ideal. Is that just due to acceptable sampling error? Or did we end up getting a sample that would really be exceptionally rare, significantly rare, if the population really looked like this? That's why we always need a significance level to define what significantly rare means. In this case, 0.01. All right, so to put that in slightly more generic terms, the overview for this section is that we will compare a known, theoretical, or hypothesized expected probability distribution with an empirically observed frequency distribution. I suppose either one of these could be, this frequency distribution could be a probability distribution as well. But the query is to see whether the observed proportions fit the expected proportions. The null hypothesis will be that all of the real-world proportions match the expected or claimed proportions. In other words, when I say all the proportions, I mean in this example, the A's, B's, C's, D's, and F's. So the null hypothesis would say, basically, this number of A's represents about 10% of the total. 18 B's represents about 30%. 12 C's represents about 30%. Etc. Or if they're off by a little bit, it's within a reasonable sampling error. The alternate hypothesis is that at least one of those proportions, whether it be the A's, the B's, the C's, or whatnot, does not match its claimed value. So in other words, that would say that some of the grades are under or over represented. Okay, how do we answer the question? We run the test on StatCrunch, of course. The test statistic, it's hard to say, in this type of problem is the chi-squared distribution, which we haven't seen very much before, but we have been introduced to it. So chi-squared is, if you recall, a right-skewed distribution. Its critical value, chi-squared star, will be either stated in the problem or found in a lookup table. These lookup tables often use a phrase called the degrees of freedom, and in this kind of a problem, the degrees of freedom is defined by the number of categories minus 1. All right, so before we get to the actual StatCrunch part here, let's go back to the example and follow get as far as we can with what we know so far. So the question again is, does the ideal distribution up here appear to be a good fit for the real observed grades? State the hypotheses. So as we've indicated, the null hypothesis is basically that all of these proportions, the A's, B's, C's, D's, and F's, are a good match for the expected fit. Okay, so here are a couple of different ways of writing that null hypothesis, one in plain English and then another in statistical symbols. The population is distributed according to the expected distribution. So the proportion of A's is 10% and the proportion of B's is 30%, ... and the proportion of F's is 10%. So the population fits this table. The alternate hypothesis would be at least one of those population proportions differs from the expected distribution. So in other words, the proportion of A's is not 10%, or the proportion of B's is not 30%, ... or the proportion of F's is not 10%. All right, now we need to get a critical value, a cutoff point, to describe our 0.01 significance from this lookup table, a chi-squared lookup table. And again, and this kind of a table will be given to you in your homework set if you need to find it. So the area to the right of the critical value, that's another way of saying the significance. This problem is 0.01 significance, so we're going to be looking at this column here. The degrees of freedom, again, is defined by the number of categories minus 1. In this problem, we have A, B, C, D, F, that's 5 categories, and that corresponds to 4 degrees of freedom. I'm trying to get fancy with highlighting here. Okay, so if we follow that over, we get a critical chi-squared value of 13.277. Plot this visually. So here's a chi-squared curve. We've just found out that a score of 13.277 will cut off a right tail with area of 1%. So it's going to be pretty far out here. So the critical value is going to be, let's just mark it here. There's not really a good sense of scale. But this cuts off the upper 1% of the curve. Now, again, as with the R scores before, it's not very clear-cut exactly what scores are being piled up here. But let's just understand that they are related to this distribution. The math behind it is pretty sophisticated, and we won't be tested on those details. But there is some kind of a chi-squared distribution going on, and we know now that if we look at our sample, and if our sample ends up having a chi-squared value that's higher than this, then that's significantly high enough to reject the null hypothesis. Okay, so now we need to find out what the test statistic actually is for our sample. And this is where we get into StatCrunch, which will also give us the associated p-value. And of course, we can also reject the null hypothesis if this p-value ends up being smaller than this 1%. So on StatCrunch, as indicated on the lecture notes here, the outline, the steps to follow will be stat, goodness of fit, chi-square test. StatCrunch will display the chi-squared value and its p-value, and it'll even give us the expected frequencies in a sample of this size. I've entered the data here in StatCrunch. So for A's, B's, C's, D's, and F's, we have these expected proportions in percents, and these are the values that we actually observe. All right, so let's follow those steps. We're going to go to stat, goodness of fit, chi-square test. It's going to ask us, where are the observed values? Okay, well, I called this column observed to make it easy to find. Where are the expected values? Well, okay, those are the expected proportions. By the way, some problems ask you to find out if all the proportions are the same. That's kind of a common null hypothesis. So rather than listing out 10, 10, 10, 10, 10, 10, 10, etc., you might, in some cases, need to click this button that just says, well, we would expect that all cells would come in equal proportions. But in this problem, we did have a given distribution. Okay, and then we can click Compute, and we get a pretty nice compact display here. What we see is the chi-squared value and its p-value, and then the expected distribution that we would get if we were really following this ideal pattern. So let's take a look at this table first. I think it's pretty interesting. What's going on here is, remember that the chairwoman sampled 40 actual grades. So these values over here are percents, and these are frequencies out of 40. So if we actually had a sample of size 40, and if that sample really followed these percents, then we would expect to get this number of A's, B's, and C's, and so on. We would expect 3.9 A's, 11.7 B's, 11.7 C's, and so on. So you can kind of see at a glance how they compare it to what we actually observed. It kind of looks like, the A's maybe are a bit underrepresented because overrepresented because we observed 8 of them, and we really only would have expected about 4. We observed 18 B's, we were only expecting about 12. That looks like it's a bit overrepresented too. We observed 12 C's, which is exactly what we'd expect. The D's appear to be underrepresented. Okay, so you can see that at a glance. But of course, when we look at things at a glance, we don't really have the mathematical brain power to figure out if things are really out of place at the 0.01 significance level. In order to do that kind of test, we need these exact numbers for the chi-square and the p-value. So let's see what happens if we plot these. The chi-square value that we ended up getting out of this sample was about 17.7. Let's see what that looks like if we plot it here. About 17.7 is going to be further out. So I've just gone ahead and entered that here. The chi-squared value that we actually got from our sample was 17.7, which is farther to the right than our critical value. So you can see that if the null hypothesis were true, this sample would be pretty unusual, very far to the right, farther to the right than our cutoff acceptability. And that gave a p-value represented by this area that I'm attempting to highlight in yellow here. That was also pretty small. The p-value is 0.0014, only about 0.1%. All right, so our chi-squared value was about 17.7. Its p-value was about 0.001, and we plotted them above here. So compare or conclude in plain English. Okay, so we can see that if the null hypothesis were in fact true, which is what this curve represents, then the sample that we got, which is represented by this point, would be significantly large. Large enough to, far enough away from the middle, atypical enough to conclude that null hypothesis probably isn't true. We've rejected the null hypothesis and accepted the alternate instead. So I'm going to propose wording something like this. Chairwoman Chandra has found sufficient evidence to warrant rejection of the null hypothesis and accept the alternate hypothesis instead. It seems that the UMGC math grade distribution is not performing according to her ideal. A's and B's are overrepresented, while D's and F's are underrepresented. Well, then you better hurry up and take a math class at UMGC before Chairwoman Chandra has her way and brings the better grades down.